This is section 5.2, part 2. We're going to talk about two things today, multiplicities and similarity. There are two definitions of multiplicity. We've got algebraic multiplicity, and that's its multiplicity as a root in the characteristic equation. I'll explain that below. And then the geometric multiplicity is the dimension of the eigenspace. That's the null space of A minus lambda I. And it can be shown that the GM is always less than or equal to the AM. All right, so here we go. Fill in the table if a matrix A has characteristic equation this. So we want to write down the eigenvalues and the algebraic multiplicity of each eigenvalue. So let me rewrite this as lambda minus 1 squared. Think of lambda cubed as lambda minus 0 cubed. And think of lambda plus 2 as lambda minus negative 2. And that's to the 1 power. And that equals 0. So the eigenvalues are the roots of that equation. The eigenvalues are 1, 0, and negative 2. The algebraic multiplicity, those are the exponents. So these numbers here are the algebraic multiplicities. So the algebraic multiplicity of lambda equal 1 is 2. 0 has AM 3, and negative 2 has AM 1. And we're going to be interested in the next section on when the geometric multiplicity is equal to the algebraic multiplicity. So we have to be able to find both. So we've already seen how to find algebraic multiplicities. Let's look at geometric multiplicities. So here's an example. You have a homework problem like this. You're given a matrix, and you want to find K such that the geometric multiplicity of lambda equal 5 is equal to the algebraic multiplicity. All right. When you have a triangular matrix, the eigenvalues are the numbers on the main diagonal. So we know lambda equals 5 is an eigenvalue, but to find the let me back up. Let's first write down the characteristic equation of A. So what I did is I wrote down A minus lambda I. And so the characteristic equation is the determinant of that matrix. But that matrix is triangular, so the determinant is simply the product of the diagonal entries. So 0 equals, I've got 5 minus lambda. So I'm going to go 5 minus lambda squared. And then I've got a 3 minus lambda and a 1 minus lambda. All right. And so the algebraic multiplicity of lambda equal 5 is 2 because that's my exponent. Now I want to find K so that the geometric multiplicity is 2. Now the geometric multiplicity is going to be the dimension of the null space of A minus 5I. So we're looking to count free variables because each free variable will add a dimension to the null space. So what I do is I take A minus 5I, augment it with 0, and I want to reduce that matrix enough to look for free variables versus leading variables. So I don't have to go all the way to reduced echelon, but I do have to do, let's see, I'm going to go 0, I'm going to leave the top row alone, and then I will multiply the top row by negative 1 and add it to the second row to kill that 2. So that'll give me K minus 6, positive 1, and then 0. And then I'll leave the next row alone. And then I'll use the third row to completely obliterate the fourth row. So in terms of pivots, I've got 2 pivot columns. And I want 2 non-pivot columns. So the only way I'll get 2 non-pivot columns is if K is 6, because I don't want to pivot here. So I'm going to need K equals 6. Okay, so here's one for you to try. Pause the video and go through the steps here, and then we'll come back and do it together. Okay, the matrix A minus lambda I is 2 minus lambda, 0, 0, 0, 5, 3 minus lambda, 0, 0, 9, 1, 3 minus lambda, 0, 1, 2, 5, negative 1 minus lambda. The characteristic equation is the determinant of that matrix set equal to 0. Now, this is a lower triangular matrix, so I can just write down the determinant without doing any calculations. I just multiply the diagonal entries. So combining like terms, I've got a 3 minus lambda squared. I've got a 2 minus lambda. And then I have negative 1 minus lambda. Negative 1 minus lambda. And we're going to use that to fill in the chart. So our eigenvalues are 3, 2, and then be careful. Think of this as negative 1 times lambda plus 1. So negative 1 is an eigenvalue. And the algebraic multiplicities are the exponents. So 3 has algebraic multiplicity 2, and the other two guys have algebraic multiplicity 1. Okay, so find the geometric multiplicity of lambda equals 3. So I need to look at A minus 3i augmented with 0. Okay, so A minus 3i, that's going to be negative 1, 0, 0, 0, 0, and then 5, 0, 0, 0, 0, 9, 1, 0, 0, 0, 1, 2, 5, and then negative 1 minus 3 is negative 4, 0. Okay, need to do some quick reductions here. I'm going to kill off all these numbers. Negative 1, 0, 0, 0, 0, and then 0, 0, 0, 0, 0, 0, 1, 0, 0, 0, 0, 2, 5, negative 4, 0. All right, now I'm going to move that 0 row to the bottom, and I'm going to use this 1 to kill that 2. So I'm going to do two things at once. Negative 1, 0, 0, 0, 0, 0, 1, 0, 0, 0, 0, 0, 5, negative 4, 0, and then 0, 0, 0, 0, 0. Pivot, pivot, pivot. We've got one free variable, so the GM is 1. So the AM was 3, no, the AM was 2, and the GM was 1. Similarity. Here's the definition. If A and B are square matrices, A is similar to B if there's an invertible P such that A is PB P inverse. The way I remember the order is I think like a cop show, you put out an APB on someone. So it's APB and then P inverse. But the good thing is similarity is like marriage. If I'm married to my husband is married to me. So if A is similar to B, then B is similar to A, and you can just say A and B are similar. here's a quick check for similarity without having to find an inverse. Here are two matrices A and B, and I'm claiming they're similar because with P equal to this matrix, A is PB P inverse. Now, we could check that directly, but that would require finding P inverse and then on this side multiplying three matrices together. Nobody wants to do that. So multiply both sides of that equation by P and just check this. Is AP equal to PB? Well, I don't know. Here we go. It will be. Let's see, dot this row with this column, that gives us a 2, and then we'll have a 3, and then we'll have, when I look at the second row, -2 plus 4 is 2, and then -2 plus 8 is 6. All right, now let's do PB. I'm going to use this as a tip here. When you multiply by a diagonal matrix, it scales the columns of the first matrix. So this first column gets scaled by 2, 2, 2, and the second column gets scaled by 3, 3, 6. So that's a quick trick. And we've seen this before, but if you multiply on the left by a diagonal matrix, 0, 2, 0, 3, 1, 1, 1, 2, it doesn't scale the columns, it scales the rows. That would be 2, 2, 3, 6. So right multiplication scales the columns, left multiplication scales the rows. Hang in there, guys, we're almost done. If A and B are similar, they have the same eigenvalues. And that's because they have the same characteristic polynomial. However, they don't necessarily have the same eigenvectors. So they have the same eigenvalues, but not necessarily the same eigenvectors. And to illustrate that, I'm going to show you that the vector v here is an eigenvector for one of the matrices B or A, but not the other. And we know that A and B are similar because we just showed it above. So let's check BV. BV is 2, 0, and that's twice 1, 0. So V is an eigenvector for B with eigenvalue 2. All right, but let's check AV, and we get 1 and then -2, and that's not any multiple of 1, 0. So V not an eigenvector for A. So A and B have the same eigenvalues, not the same eigenvectors. And then lastly, it's a one-way theorem. A and B are similar, they have the same eigenvalues. If they have the same eigenvalues, they're not necessarily similar. So it's a one-way theorem. And I put the proof of that at the end. It's not very interesting. And I'll just leave you with a comic, which I don't really understand. Mathematically, I understand it. It's an eigenvalue, eigenvector joke. I just don't really understand why it's funny or what they're trying to get at. So if you can make some sense of it and let me know, then that would be great. All right, the end.